So let's talk about implicit differentiation. Implicit differentiation. Taking a derivative implicitly. So how do we do that? What does this mean? Implicit differentiation. So if there is something called implicit differentiation, that implies there's also something called explicit differentiation. And that's what we've been doing. Explicit is when you have f of x equals some function of x, and you do the derivative of that. Right? This is explicit differentiation. This is a function, and this is the derivative. Right? The explicit derivative. Explicit derivative. Explicit derivative. Derivative. So a regular derivative, like an explicit derivative, is you have an equation, a function, a regular function, and then you do the derivative like normal. No problem, no issue. It's a function, it's a y, it's a direct function of x. A function of x. It's a direct function, normal situation. But sometimes we have equations that are not just functions of x, right? We have these implicit equations. Implicit equation. It's a implicit equation. An implicit equation or an implicit function implicit equation or an implicit function has an x and a y, but it's not, how do you say, it's not directly a function of x. Like the y, it's not y equals, right? X and y are mixed together. In an implicit equation, you have a function where it's x and y mixed together. For example, something like x squared plus y squared equals 16. This is an implicit function. This is an implicit function. It's an equation, right? It's an equation. We know how to read. We can see this equation. We maybe know what this equation makes. But x and y are mixed together. Maybe the y is squared. Maybe it's like multiplying x and y. Or you can have something like 2xy plus x squared minus y squared equals 5. This is an implicit function. It's not a direct function. It's not an explicit, right? Explicit where it's like a y equals x equation. This is now a little bit more complicated, a little bit more sort of strangely wiggly graph. This is some more complex equation here. And we call those kinds of equations implicit functions. We can solve this. We can make a table. This is like a regular situation. We can make a table maybe. We can sort of graph what this looks like. But it's not direct. It's not a direct equation where we have x and y separated, where the y equals some function of x, right? But we still find these equations to be important and useful, and so it would be helpful to be able to find derivatives of these equations. So we have to figure out a way, doing implicit differentiation, to find derivatives of this. Now I'm going to remind you, remember, a derivative of y, derivative of y with respect to x is dy dx. When we say derivative, this is the kind of thing we're talking about, right? We mean a derivative of y with respect to x. With respect to x. Meaning it measures how y changes compared to how x changes. And when we say derivative, this is generally what we mean. We're looking for the change in y compared to the change in x. The derivative of y with respect to x. How does the y value change compared with the x value changing? How does the y change compared to how the x change? And this is what we mean by derivative. Generally, we mean dy dx. There can be other derivatives. You can take the derivative of area with respect to radius. You can take the derivative of speed with respect to time. You can take the derivative of lots of things. But generally, when we say derivative, we mean dy over dx. The derivative of y, the change in y, over the change in x. How y changes compared to how x changes. Is y increasing as x increases? Is y decreasing as x increases? How is y changing? How much does y change as x changes? Is x going up very quickly? Is y going up very quickly? Is y going down very quickly or very slowly? Or is y flat? Is y not moving at all? Right? That's a zero. So this is what we mean by derivative. We're changing. How does y change with respect to x? So we can use this definition. We can use this definition to find implicit derivatives. We can use this definition to find implicit derivatives. The definition of dy dx. Use this definition of a derivative to find some implicit differentiation. So how does that work? Let's do an example. Let's say I want to find the derivative of what's a good equation? Yeah, let's do x squared plus y squared equals 16. So we're going to find the derivative of this implicit equation using our definition of derivative. Definition of derivative is change in y over change in x, dy over dx. And here's an equation. Here's an implicit equation. X squared plus y squared equals 16. Let's find, and I want you to find dy dx. Or you can also say that's y prime, right? dy dx, y prime. It's kind of the same. Sometimes they write it in both these different ways. Dy dx and y prime is the same thing. So I want to find the derivative of y with respect to x from this equation. I want to find the derivative. How do we do that? Well, when we do derivatives, every time we've done a derivative so far, we've taken an equation and we've just done a derivative, right? We've just done the derivative of this equation. We're going to do that same thing here. For this equation, what we're going to do is we're just going to take the derivative with respect to x. We're going to do d dx. Take the derivative with respect to x. WRT is with respect to. So we're going to do the derivative of this equation, d dx. We're going to d dx this whole equation. And we're going to follow the rules as we've learned them so far of all these different parts of this equation and just do the derivative. One of those pieces that's going to come out of this is going to be a dy dx. We're going to find dy dx somewhere in this equation, somewhere in our derivative will be a dy dx. And then we'll have to solve for that piece. So we're going to do a derivative of this. What does that look like? d dx of this whole thing. Take a derivative with respect to x. So let's do the derivative of x squared. What do we know about the derivative of x squared? Well, it's got x, right? So this is a normal situation. We're just going to use our power rule. Bring the 2 down in front. Bring the 2 down in front. And 2x. We did our power rule, right? So that's the derivative of 2x. Now, another secret thing that's going to happen here, like a thing that we have been doing this whole time that we've not really been paying attention to, is we actually need to do the chain rule to this problem here, this x squared. I need to do the chain rule, right? Look at this, I have an inside part and an outside part on this x squared. If you think about it, right, my outside part is the squared, the power of 2. So I did my outside derivative. I took the 2, brought it in front, and left the inside part alone. So I'm doing a chain rule to this. So I did the derivative of the outside. All right, so I'm doing, like, this x squared is kind of, I can think of it like a chain rule that I'm doing here. I did my derivative of the outside, which is the squared part. Now I need to multiply by the derivative of the inside. Well, the inside is just x by itself. And when I do a derivative with respect to x of x, when I do d dx of x, I'm taking the derivative of x with respect to x. I'm taking the derivative of x with respect to x. And what is the change in x over the change in x? Well, that, we know the derivative of x, I said this before, was equal to 1. And that's why it's equal to 1, because it's dx over dx. It's the change of itself over itself, and two things divide the same, they become a 1. So we have been doing this entire time. Every time you take a derivative of x, you do this chain rule process. It's just that every time it becomes a 1. I mean, the derivative of x with respect to x always becomes a 1. It's the same thing over itself. So we've kind of ignored doing this because it hasn't really mattered yet. It hasn't mattered with x. But it's going to matter with y. So let's do the same thing. Let's do the same rule with y. Okay, so this 2x times dx over dx, which is 1, which we can safely ignore. The derivative of x squared was 2x. We did that. Great. Let's do the same rule, d dx of y squared. And again, I'm going to think of using this like a chain rule. So I got my derivative of the x part plus, just doing the derivative of each piece. I'm going to do the derivative of the outside of the y part. Right? I'm going to use my power rule, doing the derivative of the outside. Take the 2, bring it in front, leave the inside alone. This is my chain rule. Right? Take the outside derivative. It's going to be a 2y. Okay? 2y. Derivative of the outside. And now I need to multiply that by the derivative of the inside. The inside of this section is this y by itself. So we're doing the chain rule. We're finding the very inside. We did the outside was the 2, the squared part. Derivative of the outside, which is our power rule. Bring the 2 down in front. Leave the inside part alone. Leave the y alone. That's my chain rule. And now multiply that, derivative of the outside, times derivative of the inside, which is just the y. I'm doing the derivative of y with respect to x. I'm doing d dx of y. And this is going to become dy over dx. And there's the thing I want to find. This is my dy dx. This is my y prime. This is where it pops out when doing this derivative. So I'm going through the whole equation, doing derivatives as I go, using the same rules that I've done before. So I got 2x, right, derivative of this x part, doing my chain rule, derivative of the outside, which is just the power rule, 2x, times dx over dx, which the derivative of x, right, which is just 1. So it's really just 2x. Plus the derivative of this y squared. Do the chain rule again, derivative of the outside, 2y, times the derivative of the inside. Now I'm doing the derivative of y with respect to x, which is dy dx. So that's the y derivative, equals derivative of this 16, of the number here. Remember, I'm doing the derivative, I'm doing dy, I'm doing d dx of the whole equation. So the derivative of 16 is a number that's going to be a 0. So I've done my derivative of this whole equation. I did it piece by piece, following my rules of my derivative. Any questions about this process so far? All the rules we know, we're just applying those rules the same. We do the chain rule, which involves our power rule here. Nothing really new. The only new part is when I do the derivative of y, I'm doing this d dx, I get the dy dx part right here. I have my derivative part right here. So we're going to clean this up a little bit. So this is just going to be 2x plus 2y dy dx equals 0. I don't need my dx over dx. That's a 1. That can be safely ignored, right? 1 times 2 is 2. Same things. So it's fine. So I got my implicit differentiation. Now I have to solve for dy dx. I want to get the dy dx part. I want to get this part alone. I want to get that part by itself. Oops. Draw a better circle. I want to get this part by itself so that I know what the derivative is going to be. So I can find the derivative of this equation. I want to know dy dx. So I'm going to have to do a little bit of rearranging. This is algebra, right? I want to get this by itself, so I got to cancel all the stuff on this side, move it over to this other side. I got to move all this stuff over here and get the dy dx by itself. So I'm going to minus this 2x part, move that away. Right, just solve for dy dx. I got 2y dy dx equals negative 2x. And then I got to cancel this 2y. So I'm going to divide by 2y. Divide by 2y. Cancel the 2y. I'm going to get dy dx equals negative x over y. Cancel my 2's here. And that's your answer. That's your derivative. So you're getting dy dx in this implicit equation. You're getting a derivative by just taking derivatives, the same rules that we've applied so far, the same rules, right? We just did the same rule. We just did our power rules, and we did our chain rule, and we got this dy dx part that popped out in the equation. Once I get that dy dx part in the equation, I solve for dy dx. I get the dy dx by itself, and then I get my derivative. Now, one thing that's interesting to note here, a little interesting note. Note. In my derivative has x and y. The derivative depends. Derivative depends on the value of x and y, right? Because both of those are in the equation. And that's a unique feature of implicit differentiation. Implicit derivatives, oftentimes the derivative will have an x and a y variable in the answer. And so your derivative will depend on not just the x position, but also the y position. Both of those have an influence in the derivative. Derivative, why am I this weird word here, derivative. Derivative depends on x and y. So going through this again, sure, let me explain that one more time. So again, doing this derivative here, we're doing the change of this function with respect to x. We're doing ddx of this whole equation, right? So we're looking at how these variables, how these numbers change with respect to how x changes. We're doing ddx. We're taking the derivative with respect to x. So as we go through, we're looking at how these change with respect to x. So in the first part, with this x squared, if I imagine doing like a chain rule here, I have this x part on the inside, I have a squared on the outside. So I do my chain rule, I do the derivative of the outside, which is the 2 times this inside part of x, 2x, just the same derivative we've done before with x squared, 2x. Derivative of the outside, times the derivative of the inside. The inside is just the variable x. So derivative of the outside, 2x, times the derivative of x. And I'm taking the derivative of x with respect to x. I'm doing remember, we're doing ddx. So the change in x with respect to x is dx over dx, because the variable is x. We're doing the change of x. We're looking to see how x changes. with respect to x? Well, the way x changes with x is it changes together. It changes as a 1. So the variable is x. Whatever the variable here is, it's going to go over dx, right? D, whatever this is, over dx. If this was an a, or a q, or a t, I would do dt over dx, or dA over dx. Whatever the variable I'm looking at is, I'm looking to see how that measurement changes. This was a y, right? So I'm looking to see how the y changes. Whatever the variable here is, it's going to become that variable over dx. So with x, it's dx over dx. It becomes a 1. With y, it's dy over dx. If it was a t or an r somewhere in here, it'd be dr over dx. I'm looking to see how the whatever variable changes with respect to x. Okay, so we got this dy dx. We got our equation, and the derivative here depends on both y and x, a unique feature of implicit differentiation. Okay? Hold on. How much time do we got? What do we got here? 11:25. Okay, I got about 10 minutes. Great. Let's do one more example. Let's do this problem here. Find dy dx of this equation here. Let's do y squared plus 2xy plus x squared equals 1. Y squared plus 2xy plus y squared equals 1. Find the derivative, find dy dx of this problem here. So, this is an implicit equation. We are going to do ddx of this equation. And we're going to follow through and find out what our derivatives are. And we're going to isolate the dy dx part and solve for that dy dx part to get our answer. So doing this derivative, again, we use our chain rule idea that this y is a chain rule part. So I'm going to do the derivative of the outside times the derivative of the inside. So it's going to be 2y, derivative of the outside, bring the 2 down, chain rule, right? Power rule, times 2y, outside, times the derivative of the inside, there's the y, so doing ddx of that is dy dx. There's my dy dx. Derivative of the outside times derivative of the inside. So every time there's a y, you're going to eventually get to the point where you're going to have a dy dx, right? Because it's going to do whatever derivatives of the outside parts all the way into, once you get to the y, you're going to get a dy dx. So 2y times dy dx. That's that one. Plus, here is 2xy. How do I do a derivative of this part with an x and a y multiplied together? What kind of rule, what kind of thing can I do here? Anybody think they know what kind of rule might apply in this situation? Two things, it's 2xy all multiplied together. What rule do we know? What rule can we think of where we can use, what rule can we use to do the derivative of these two things being multiplied together? Being multiplied together. What rule do we know can we use when two things are being multiplied together? You're leaving me hanging here, everybody. Multiplying things together. Is it a product rule? Thank you, Jessica. Yes, we are going to use a product rule for this. We have to use a product rule. It's a 2x times a y. This is my f and this is my g. I have to use a product rule here to deal with the x part and the y part separately. I need to do a derivative of the x and a derivative of the y. There's two variables here. I got to do each one. They're separate pieces. So I'm going to go my product rule. My product rule was fg prime plus gf prime. Fg prime plus gf prime. Okay, let's put this in use here. So the first times derivative of the second. Okay, that's easy. 2x dy dx. First times, right, the 2x, first times derivative of the second. Well, the first stays the same. The derivative of y is dy dx. The derivative of y is dy dx. So that's easy, right? First times derivative of the second. First times derivative of the second. I did my x part, I got the y part. First times derivative of the second. Plus the second y times the derivative of the first. Product rule, right? First times derivative of the second plus the second times the derivative of the first. Derivative of 2x, well, that's just a 2. So first times derivative of the second plus second times derivative of the first. When we have a 2xy, we multiply those together, we get our product rule to figure that out. Use your product rule in that situation. Separate out those pieces. So, derivative of the y squared plus the derivative of this inside part plus the derivative of the x squared. Well, we know that's just 2x. I'm not going to bother to write the dy dx here. You can imagine there's a dx over dx. You can imagine that being here. But I'm not going to be writing this all the time. Right? I didn't write it for the 2x part. I didn't write it, We can imagine there's a dx here, but we're just going to do the derivative of the x squared like normal. We're just going to get 2x. I don't need you to write that. No one needs you to write it. It's fine. That derivative equals 1. Equals 0. Derivative of 1 is 0. So, very good. We got this whole thing. Let's clean this up a little bit. 2y dy dx plus 2x dy dx plus 2y plus 2x equals 0. So now we have to solve for dy dx. Get the dy dx by itself. Problem is here, there's 2 of them. It's an x, everybody, that's an x. Problem here is there's 2 of them, and we're going to have to deal with that in a second. We'll get to that in a moment. Easy step first, I can get rid of this 2y and this 2x. Minus 2y minus 2x on both sides. Minus 2y minus 2x on both sides. I'm going to get 2y dy dx plus 2x dy dx equals negative 2x minus 2y. Right? Move these pieces over, simplify. Now, my problem here, now I have to deal with this situation of having 2 dy dx's. I only want 1 dy dx. I want to somehow combine these. Well, I can't add these together, right? Because one's a 2y, one's got a y, one's got an x. I can't combine these together. I can't get 4xy, right? I'm adding, I'm not multiplying. I cannot add these 2 pieces together because one's got a y, one's got an x, right? They're not like terms. They're not like terms. So if I can't add them together, I have to get this dy dx sort of alone. What we're going to do, a trick that's very often used, is we're going to factor out the dy dx. We're going to bring it outside as one piece. Dy dx on the outside. And then we have this 2y plus 2x. And we have isolated the dy dx alone. That's a really messy word there. Factor out. Factor out the dy dx. And now I've got one dy dx all alone. And I can cancel this parenthesis here. Well, it's a multiplication, so I cancel multiplication by dividing by this whole parenthesis piece on both sides. 2y plus 2x on the whole thing. So I'm going to get, oopsies, I'm going to get dy dx equals negative 2x minus 2y over 2x plus 2y. And that is my derivative. Easy, right, everybody? No problems. So we're doing implicit differentiation, right? We're doing derivatives. The only difference, the only new thing that we're learning here is that we have this dy dx part. And there's a y variable in our situation now. So we're going to have to deal with that. We're going to have some practice with this. I don't have an assignment for you today. However, we're a little bit past our time, so I'm going to let you go. But tomorrow, I am not going to be here tomorrow. You'll have a sub again. Apologies, everyone. I'll explain why later. But you will have, I'm going to assign you some problems in Edgenuity. A specific section of Edgenuity where it talks about implicit differentiation. I want you to watch the videos. I want you to practice the questions tomorrow in class. So you'll be doing Edgenuity on this implicit differentiation, watching those videos, reviewing this material, and the assignment will be answer the questions in that Edgenuity assignment. There's one video to watch, maybe like 2 questions to do, something like that. So you'll be doing that tomorrow in class, watching that Edgenuity and working on that. So hopefully that video will help. Hopefully this will help. But that's it for us today, everybody. In the chat, type goodbye. Once you type goodbye, you're free to go. I will see you next time on Thursday. Good job, everybody. See you next time.